A new observatory scanning our skies and a check-in on Mars. You're listening to Are We There Yet? The radio show exploring space exploration. Hi, I'm Brendan Byrne. Astronomers now have a new way to peer into the cosmos. The Vera C. Rubin Observatory. This new observatory, built on a mountain in Chile, will capture incredible new images, track near-Earth asteroids, and observe things like dark matter and dark energy. We'll speak with Embry-Riddle Aeronautical University's Ted von Hippel about the power behind this new telescope. Then, NASA's Curiosity and Perseverance rovers continue to explore Mars, searching for ancient signs of life. They're now exploring areas of the red planet that have signs of past water activity. We'll speak with the University of Florida's Amy Williams for an update on the exploration of Mars. That's ahead on Are We There Yet? On a mountain in Chile, a new observatory is scanning the skies and taking images of everything from nearby asteroids to galaxies light years away. 8 meters in diameter, the Vera C. Rubin Observatory can capture about 100 times more sky than some other smaller scopes or observatories. And plus, it's not just taking cosmic observations. It's also studying things like dark matter and dark energy. And all of these incredible new images can be accessed right from your phone. Here to talk more about this brand new observatory is Ted von Hippel, a professor of physics and astronomy at Embry-Riddle Aeronautical University. Ted, welcome to the show.
Thank you very much, Brendan.
Hey, so a new observatory came online. Tell us a bit about why the scientific community is so excited about this new observatory.
It's a super exciting observatory. As it happens, I attended a rollout for the Vera Rubin Observatory at the American Astronomical Society meeting 2 weeks ago in Anchorage, Alaska. I've also been following this for quite some time because I want to use it for my own science. The reason why the community is so excited is that there's a very broad range of science that it will do and can do. Its primary goals are to look for near-Earth asteroids, which have very practical applications for those of us who live on this planet, i.e. not getting hit by something big when we don't expect it.
Yes.
And it has more esoteric goals, which is to study the dark matter and dark energy distribution and what it means, as well as a whole lot of projects on the Milky Way and stars that change their brightness suddenly, like supernovae or novae or just regular variable stars. The Vera Rubin Observatory has the potential to discover US, Chinese, and Russian spy satellites. And
how does it do that? That is pretty interesting.
It's not on purpose. Because it's taking very deep pictures of the sky over and over again, satellites during dawn and dusk are illuminated by the sun. And so there's a reflection off of them, and it's easily going to pick up essentially all spy satellites or all military things that our government doesn't necessarily want us to know where they are. And so in order to deal with that, the data are shipped from the Rubin Observatory, actually through a number of hops, first to a town called La Serena in Chile, then to Santiago in Chile, then to Miami, then out to California, and then processed on a computer, at a giant computer at an undisclosed installation that's owned by the US government. And those satellites will be removed from the data. Then the data are passed on to the astronomers. And we don't get access to the full data for something like 80 hours, about 3 days, because on that timescale, the US could have moved their secret satellite to a different orbit. And so they no longer care if we know about it.
Ted, I want to go into the things that it is going to be looking at. But first, I want to stay a little bit closer to home and talk about where this observatory is and why that is so important to the things that it is going to see. Where is this observatory at, and why is that an asset to astronomers?
Yes, it's in the Atacama Desert in Chile, primarily U.S. telescope, but the U.S. has a long history of working with the Chileans because they have a fantastic site in the mountains, and we have a number of observatories there. It's very dry, the weather is very good, the air is very stable, and all of that makes for excellent image quality. So this is a survey instrument that's going to look at a giant piece of sky in each view. It has a very, very large camera, and the image quality is immensely important to it. So that's where it's sited.
To compare it, I have been to your observatory at Embry-Riddle University in Daytona Beach. What size is that telescope? And then what size in comparison is the Rubin Observatory?
So our telescope is a 1 meter telescope, which means the primary, the largest and first mirror the light hits, is 1 meter or 40 inches or just over 3 feet in diameter. The Rubin telescope is about 8 meters in diameter. Also, our telescope has 2 main mirrors, a primary mirror at the bottom where light hits, bounces off, hits a secondary mirror, which is quite a bit smaller. The Rubin telescope, in order to have the very large field of view, has 3 mirrors, a primary, secondary, and then a tertiary in a more complicated system. This is necessary to give the very large field of view, because if you use a telescope with a design like ours, a Cassegrain or Ritchie-Chrétien, if you've heard of those terms, that will give you a smaller and smaller field of view, what you can see, the angular extent of what you can see as the telescope gets bigger and bigger. So this being a giant telescope, it needs a different design to have a wide field of view, and that, therefore, the 3-mirror design.
The one thing you mentioned was looking for near-Earth asteroids. I'm going to assume that that's because it's looking at a large swath of the sky, and astronomers like yourself can look for changes, like objects that are hurtling towards us, right?
Yes, exactly. Again, to compare to the Embry-Riddle Observatory, the telescope would deliver a field of view about the size of the moon, full moon, which is half a degree on a side. This telescope, the Vera Rubin telescope, delivers a field of view that's 3.5 degrees across, which makes it almost 10 square degrees and many, many times bigger than what we could see, which is half degree by half degree, therefore a quarter degree. And it has a giant camera made by the Department of Energy. We have, for instance, at Embry-Riddle, a 16 megapixel camera. The Vera Rubin Observatory's camera is 3 gigapixels. So that's 3,000 megapixels. It's just a gigantic detector. And the reason is, again, you want to look at as big a possible piece of the sky as you can in one go, so that you have many more stars, many more space in which you could capture a near-Earth asteroid.
How do you go about analyzing something like that? I mean, is it astronomers that are just zooming in very, very closely to different parts of the images and looking for changes in it? Is this automated? Is there computing power? What goes into actually looking at all of this data and coming up with like actionable observations?
Back in the 1930s, Clyde Tombaugh found Pluto by using a blink comparator. There's a photograph, and he's looking in one eye at one photograph and another eye in another photograph, and the 2 photographs are taken at different times, and he's looking for something moving. There's no way to do that in the modern era with the millions of objects that we want to look at simultaneously. So this is a massive data processing enterprise, and astronomers have become very, very good at seeing whether little points of light get brighter or fainter or go away or move. And so all of this is done on the computer with some preset algorithms.
Okay. So yeah, so I couldn't imagine staring at that two different eyepieces. That would be massive. Let's talk a little bit about another thing that you mentioned that this observatory is going to help with, and that's uncovering and understanding dark matter, right? Tell me a bit about what that is and how observations from the Rubin Observatory are going to help physicists like yourself better understand.
Dark matter we've known about. In retrospect, we sort of had the first hints in the 1950s, but Vera Rubin plays a key role in the understanding of dark matter. In the 1970s, she was studying other galaxies, first Andromeda Galaxy, which is the nearest major galaxy to us, and she was looking at the motions of stars in those galaxies, and she was finding that the motion didn't make any sense based on all the matter we knew about. Some of the stars were moving too fast, as if there was more matter around than we could see. And this problem has persisted, and to this day, there is an immense amount of evidence that there's some other type of matter out there that we cannot see. So all the matter that we can see, the stuff in the periodic table, hydrogen, helium, lithium, beryllium, carbon, oxygen, that stuff we can all detect. But there's something else out there that is adding to gravity, and this is what we call dark matter. We don't know what it is. It's been a massive undertaking of astronomy and physicists for the last 40 years to try to figure it out, and we still don't know what it is. So the Vera Rubin Observatory is meant to study this, and in part by studying certain types of objects that will tell us something about the structure of dark matter in the universe. And that includes things like gravitational lensing, that includes supernova. All of these things map out the universe for us.
And is that because of just how wide of a view this telescope is capturing, that you're able to look at these things?
Yes, the wider the field of view, the more of these things we're going to get at any one time. And so right now we need thousands or tens of thousands of these probes to make progress, not just a few.
And will our understanding, and I say our like I'm helping at all, will your understanding of dark matter, do you think that they'll come to a conclusion with this observatory, or is this just one piece in a larger pie of understanding this phenomenon in our universe?
The answer is we really don't know. When we run into a major problem in physics or astronomy or any of the sciences, we don't know when the resolution will come. My personal expectation is that the Rubin Observatory will help us learn a lot of detail about certain aspects of the dark matter problem, but that the breakthrough will come somewhere else down the line, and we just don't know where. We don't know if it's going to be a particle that will be detected by some particle machine that's underground and protected from other things, or if it'll be done in astronomy. We're going to keep learning about pieces of the dark matter problem until we have that breakthrough.
That's the exciting part of science, right? Is you never know when that next breakthrough is coming.
It is exciting. It's frustrating sometimes for people because they want to see an answer, but we're compelled, we're driven to try to figure these things out.
Another thing I want to talk about, Ted, is you mentioned at the start of this conversation, your interest in the Rubin Observatory is because you are looking to utilize it for your own research. Tell me a bit about the process of how the observatory's time is kind of given to scientists like yourself. How do you go about doing that?
Okay, so the Vera Rubin Observatory is a survey instrument, so I cannot get access to it and say, oh, please point over here. Instead, they're going to have a programmatic way of looking at the sky, one piece of the sky after another, but all the data become public. They have three ways of making the data public. One, amazingly, within about 60 seconds, they will alert for things that change in the sky, things that get much brighter or fainter or move, and that's to find near-Earth asteroids or supernovae or other things. They'll have a daily processing, and then they'll have a much deeper processing on a yearly basis. So I'm going to be using two of those. I train students how to use our telescope at Embry-Riddle, and I'm going to have some of them who are interested in supernovae or things that suddenly change in brightness sign up for the alerts that are generated. By the way, this telescope is going to generate 1 million alerts a night, so we can't sign up for all of them. We have to sort of down select or thin that with some algorithms that they're going to make available. And then I personally, in my own research, I'm going to be looking at the yearly data products to try to find the stars that I'm interested in. I work on the ages of stars, and I'm going to be looking at some very distant stars in our galaxy.
And finally, Ted, I am looking at the Vera C Rubin website at rubinobservatory.org. There are some absolutely gorgeous pictures on here as well. I mean, as a public outreach tool, how is this also going to drum up interest in astronomy? Because it is gorgeous. I found myself getting lost in these images myself. But I mean, could this also be used to get people interested in astronomy?
I think it is an excellent public outreach tool, and I think it's no surprise that the NSF and DOE had a big press release about it. You know, when you look at those images, you can see how they find near-Earth asteroids. I think that's going to be very interesting to kids who are interested or adults who are interested in this subject. There's a beautiful image of the Trifid Nebula. There's going to be many, many other beautiful objects that many objects in astronomy cover a very wide field. The Hubble has these beautiful deep snapshots, but it doesn't typically have things that cover a wide field. And the Vera Rubin telescope will be excellent at finding that. Also, all the data is in the public domain. So if people will be as it's generated. So if school kids or college students want to get access to this, there will be tools to do that.
We've been speaking with Ted Von Hippel. He's a professor of physics and astronomy at Embry-Riddle Aeronautical University here in Daytona Beach, Florida. Ted, thank you so much for joining us.
You're welcome. It's fun chatting.
Still to come, Martian news.
We're really curious, to try to piece together why do we see these discrepancies in the types of rocks that are exposed in the mountain? What does that tell us about the history of Gale Crater?
That's ahead on Are We There Yet? You're listening to Are We There Yet? I'm Brendan Byrne. What's better than a new pair of sneaks? How about new shoes that were made in space? A Florida company plans to use 3D printing and AI to make footwear in space by 2026, when the technology launches on board SpaceX's Falcon 9 rocket, taking manufacturing off the planet. That's next week on Are We There Yet? But for now, we're talking about Mars. On our neighboring red planet, the Curiosity and Perseverance rovers are busy at work and have been for years, exploring Mars and its craters, mountains, and the overall terrain of the planet. And while our rover friends climb Martian mountains, it's the scientists on Earth working behind the scenes that make it all possible. Scientists like Amy Williams. Here to talk more about what's happening with our Martian rovers is University of Florida's Amy Williams, who's also a member of the rovers science team. Amy, welcome back to the show.
Thanks again for having me back.
Well, Amy, it's been a while since you and I have spoke, but during that time, our rover friends on Mars have been very, very busy, so I'm glad you are here to tell us what they are up to. What is Curiosity doing these days?
Well, Curiosity, we've been traversing through Gale Crater and climbing up Mount Sharp for 12 years now. I always come up with these little updates, and hopefully folks can really recognize, like, when we get to a new area of this mountain, how really excited we get about it, because we've been climbing this mountain for 12 years. And so getting into new terrain is particularly exciting at this stage. And that's actually what we're in right now. We're in a place that we had only seen from orbit. It had been so intriguing for, more than 12 years, like when we were even picking the landing site. This place is called the Boxwork. And it looks like sort of, kind of like if you had little boxes stacked together, or some people have even described it as sort of like Martian spider webs. So it has sort of this network texture. It's really large scale. It's on the scale in some cases of, much larger than the rover. And, we've been climbing for so long to get to this. And it's so really neat to be there. I almost said in person, but, in rover, and to get to see these in real time for the first time. So, when you see stuff from orbit, this is how in some ways, how we pick where we want to go with our rover friends. And these features are super neat because they're formed by water. What we've been climbing through on Mount Sharp are these rocks and minerals that normally form when water is sort of drying out, and you're getting basically salts that form from that drying out water. Really cool to see this box work, because this formed deep underground. This formed when there is really a mountain above where we are now. All that material has been eroded away, and that's exposing these boxwork structures now. But they formed, billions of years ago when water was still percolating through the subsurface as groundwater. These features are really cool because they could be sort of the last gasps of water in at least Gale Crater. But you're seeing, even as water on the surface is drying out, you're still seeing these pretty active subsurface, groundwater features being formed. It's just this really neat, like snapshot into the deep history of Gale Crater.
What is Curiosity equipped with to study this, and what data can it collect to send back to someone like you to analyze this area?
So we have several remote sensing instruments that can tell us about sort of the chemistry of the rocks. And so this tells us that we're dealing with these salts called sulfates. It tells us that what makes up the boxwork is a kind of a different sulfate than what makes up the bedrock around us. So we can start to parse out sort of the different timeframes in which these waters were flowing in the subsurface or on the surface, sort of these two different environments. So we can use our laser from our ChemCam instrument in order to assess the elemental chemistry of the rocks. We actually recently got a drill sample from this area. The drill name actually was pretty special this time. So it's named Altadena. That is the name of an area in Southern California near the Jet Propulsion Lab that was actually dramatically impacted by the Eaton fires from earlier this year and the last year. And so this is sort of this homage, like Altadena is forever on Mars, because so many people who work at JPL lost their homes in the fires, and they lived in Altadena. And so you feel like it's not just you. Not only are you sharing the trauma of the fires, you've got friends to support you, communities to support you, and then we're also like sharing these names with our rover buddy on Mars. And so it's a kind of just a nice nod to what everyone's been going through the past 6+ months.
And these drill samples, these are processed on the rover itself, right? These are not like Perseverance that you'll be leaving to pick them up, right? These are processed in situ?
Yes. So we drill and we get what's called drill finds, and we can ingest that into the rover instruments. We can tell, for example, like we are able to understand what minerals were present with far more detail by ingesting those drill finds. And that's part of what tells us that what makes up the boxwork is a calcium sulfate, which we actually haven't seen for a while. We used to see much further down the mountain, kind of disappeared for a while in our traverse, and now is reappearing. And so we're really curious, to try to piece together why do we see these discrepancies in the types of rocks that are exposed in the mountain? What does that tell us about the history of Gale Crater?
You mentioned this trek up Mount Sharp, and it's hard to really fathom what Curiosity is doing in its 10 plus years on Mars. But I'm looking at an image now, and the top of Mount Sharp is somewhat like an 18,000 feet elevation change, right? I mean, this is a really really big geological structure it's climbing up, isn't it?
Yeah, so the mountain is 5 kilometers tall. And so if you think about running a 5K is maybe some listeners are, completely capable of. Maybe I need to train a little bit before I can do that. But
Same here, yes.
when you think about the rover, Curiosity drives backwards in order to protect its wheels. We're moving relatively slowly in the grand scheme of things, being careful about where we drive, taking care of the rover, battery, rover state of health. And so it takes a while to climb something like this, but we're slowed down even more by us nosy scientists who say, what's this? What's that? Let's explore this for a while. And so if we just made a beeline to the top, we could do it more quickly, but then you wouldn't have all this cool science.
Let's talk about this cool science for non-scientists like myself. Curiosity is taking some incredible images. NASA has just released this really cool 360 view of it. Can you talk to me about it as I get lost in watching this right now?
This is my day-to-day life of just like staring at these beautiful images or these panoramas. So yeah, NASA has this awesome 360 pano that we've taken of the boxwork area, and some of it's labeled so that you can zoom in on the near field boxwork structures and ridges and then the far field, and you realize sort of the scale of what you're looking at. It's enormous. This panorama is giving you a sense for, the whole rover can fit into the void space that would have been within one of these boxwork structures. Of course, this was all in the subsurface. It was solid except for groundwater moving through it. But if you think about it, like this used to be deep under the mountain, and now it's eroded away in such a way that the rover can roll across it. So yeah, if your listeners are able to dial in and actually check out that panorama, you'll get a sense for the scale. You get a sense for where we've been. There's rover tracks in the near field. You can move the panorama around and manipulate it to kind of see that. And then you can also see kind of where we're going, climbing up the mountain even further as we continue to explore this boxwork region.
Yeah, this is incredible. I am absolutely engulfed by this, and those rover tracks are so cool.
It's so
pretty
cool.
wild that
I know.
There's robot tracks on another planet. It's pretty wild. Amy, let's talk about our other rover friend, Perseverance. What's that mission up to?
Percy is still exploring outside the crater rim of Jezero. And the last few updates, we've been doing this. This is, of course, an enormous area for us to explore. But what we've been doing recently is we've actually climbed up and out of the crater, and we've kind of gone downslope a little bit so that you can see out way beyond the crater into this, what we call ancient Noachian terrain. So the Noachians, sort of the earliest phase of time on Mars when there was abundant water. And the rocks that we are exploring now, of course, they would have formed during that time. And so recently we've been exploring sort of this kind of lowish point. We've named it, I should say, the Crocodilian Plateau. The plateau has a really cool chemistry to it that looks like it is made up of, I'll use the scientific term, phyllosilicates. But a way to think of it is if you think about clay is a type of phyllosilicate. And so you can generalize this and say, oh, this is a clay-bearing unit, something that is reflecting water having interacted with this ancient basaltic terrain very, very, very long time ago. And so we've been we've got a few abrasions. We've tried to assess sort of the chemistry and understand the extent of this clay-bearing material, trying to decide where we want to get a sample of this, because this might be some of the oldest clay-bearing materials that we will find on this mission. Clay is really cool because not only does it tell you about water interacting with the rock billions of years ago, but if there is organic carbon, which I know I tell you all about each time, is a way to not only search for potential evidence of life, but to also understand, even if that carbon is not made by life, if it's made abiotically, it can tell us about sort of the building blocks for life and how present and preserved it is. So hoping to get a sample of this really cool clay-bearing material in the Crocodilian Plateau, and that's what we're sort of puttering around working on right now.
And I'm taking a look at the map of where NASA's Perseverance has been. It's up here on this plateau. It seems to be kind of doubling back a bit. Where is it going to next? Are you going to hang out here for a bit and try to find that that perfect sample of that clay?
That's what we've been doing for a little bit here. One of the things that a geologist does is when you get out to the field, you walk around a little bit and you get a sense for the context of what you're exploring, right? You want to see how far a particular type of rock extends, this way or that way. And that helps you build sort of this mental context for what layers are below it, what layers might have been above it and they've eroded away. And it helps us figure out, like you said, where's the perfect sample? Where's a sample that's going to give us the best insight into this type of rock, its potential to preserve evidence for life, but also everything we can learn about, 4 billion year old Mars. And so, yes, you will see on the map that we've gone down and then to the side and the other side and back up because we've been sort of characterizing this region. Hopefully we'll narrow down on that great sample to collect. And then we're going to continue going south for a little while as we have more of this diverse crater rim to explore.
I love the analogy of just like a human geologist, you walk around and get your bearings. That's really cool to think of Percy in that way, but there is a decision that needs to be made, and Percy does not make that decision, right? How do you come about with your colleagues and figure out where you're going to pick that clay sample out?
Oh, it's so challenging, and getting consensus on a team of several hundred people is always difficult as well. Something that my PhD advisor used to say is, if you don't cut this rock open, you're never going to be able to answer questions about it. So you can keep it pristine and never mess with it, but you won't have any answers. Or you can cut it open and you're going to disrupt sort of the structure you're looking at, but that's how you're going to answer your question. And it feels a little bit like what we do with Perseverance, where it's like you only have one tube to collect one, special sample in. How do you decide which one to get? And so it comes down to, does it have those characteristics? So in this instance, does it have the clay minerals that we're really interested in? Is it from an area we've carefully contextualized by driving around and determining where the boundaries of the bedrock are? And then also it comes down to, can we actually drill with the equipment, the technology that we have on board the rover? Some pieces are going to be too small for us to drill. And so that's always the challenge then of, there's the scientific side and then there's the engineering and technical side of getting the arm on the rock in such a way that you can safely collect the sample.
Well, thanks for breaking it down for us, Amy Williams. And until next time, keep up the great work on Mars.
Thank you so much.
That was University of Florida's Amy Williams, a member of the rovers team. You can check out our website to see a 360 image from Curiosity and take a look at the area it's exploring in Gale Crater. Visit cfpublic.org/space. And before we end the show, this summer, join the Central Florida Public Media family. We're aiming for 100 new or rejoining monthly sustainers to support the independent news and programs just like this one that you love. Become a sustainer and get a special thank you gift, like an umbrella or travel mug. Find out more at cfpublic.org. That's going to do it for this week's show. If you're not already, be sure to subscribe to the show's podcast feed so you never miss an episode. Subscribe on the Central Florida Public Media app, Apple Podcasts, Spotify, the NPR app, YouTube, or really wherever you get your podcasts. Stay connected with this show. Follow us on social media. Our handle on Instagram and Facebook is AWTY_space. And if you got an idea for a future episode of the show, or you want to join us as a guest, reach out. We're at arewethereyet@cfpublic.org. Are We There Yet is a production of Central Florida Public Media. Our intern is Ashley Reap. Our producer is Marian Summerall. Editorial guidance from Latoya Dennis. Support for Are We There Yet comes from our listeners. Until next week, I'm Brendan Byrne. Thanks for listening.